Good day, everyone. This is in continuation of our class, Web Computing and Mining, MIS 901. Week 3, Review of Data Structures, continue. Week 1 and 2, we started with linear data structure. Then week 2, we talked about nonlinear data structure, trees. And in week 3, we'll be talking about graphs. So we'll look at the graph data structures. Graphs are generalization of trees. A simple graph G, which denotes graph, is equals to VE. In bracket, V means vertices, E means edges. Consists of a non-empty set V, whose members are called the vertices of G, and a set E of pairs of distinct vertices from V called the edges of G. So the link from one vertex to the other is what you call the edge. And so we'll be looking at them from time to time. Graphs could be undirected, directed, or weighted. In an undirected graph, the edges don't have a direction. You can go either way on them. That is, you can go forward, you can come backward. You can go from vertex A to vertex B, or from vertex B to vertex A with equal ease. That is, it is bidirectional. For a directed graph, you can go in only one direction along an edge from A to B, but not from B to A. As on a one-way street, you move forward, you don't come back, so it's unidirectional. Such graphs are usually called digraphs for short, which means directional graph. In some graphs, edges are given weight. That is, you give them number to denote maybe distances or maybe some kind of measure. A number that can represent the physical distance between two vertices, or the time it takes to get from one vertex to another, or how much it costs to travel from vertex to vertex on airline route, for example. Such graphs are called weighted graph. You look at the first one, undirected graph, there's no arrow, nothing there, so it means you can move to any direction on the same edge of the graph. Directed graph, digraph, it has an arrow, meaning you move in the position of the arrow, in the direction of the arrow, and you don't go back. Weighted graph, you now have numbers denoting the weight, which might be distances, time, or even cost, as much as possible. Applications of graphs. Graphs have many applications in computing. Some of them are: 1. Finding the least congested route between two phones, giving connections between switching stations. 2. Determining if there is a way to get from one page to another just by following links. Applications of graph: finding the shortest path from one city to another. Can be in Lagos, talk of Abuja alone. What's the shortest path connecting these three cities together? So as a traveling salesperson, finding the cheapest path that passes through all the cities that the salesperson must visit. Then determining an ordering of courses so that prerequisite courses are always taken first. Graph terminologies. There are several graph terminologies, and it is crucial that you have a clear understanding of these terminologies and must be able to make some differences between them. So we are now going to be looking at some of these terminologies. First on our list is adjacent vertices. Two vertices are said to be adjacent if there's a connecting edge between them. So if there's a vertex here, another vertex here, and an edge is linking them together, you can say the two of them are adjacent. A path. A path is a sequence of adjacent vertices that is moving from one to the other to another. That becomes a path. You can trace it. You could call it a route. You move from one vertex to another, and you are going. That becomes a path. So if you have Lagos, Ibadan, Ilorin, Abuja, and they are all vertices linked together. The path from Lagos to Abuja will be the one you pass through from Lagos to Ibadan to Ilorin, then you get to Abuja. A circle. Circle is a path in which the last and first vertices are adjacent. From the last to the first, you go, you come, you go, you come, it becomes a circle. Connected graph. A graph is said to be connected if there is a path from any vertex to every other vertex in the graph. So from that particular vertex, from a particular vertex, you can go to any other vertex in the graph. So any vertex you pick, you can always visit other vertices in the graph. Then that becomes a connected graph. So look at it. This is the path 1, 2, 3, 4. Then this is the circle from 1 to 4. You can move all through. Connected graph, all the vertices are connected together. Disconnected, there is at least one vertex that does not have any link to any other vertex. So you call that one a disconnected graph. Paths and circles in a digraph. Paths and circles in a diagram must move in the direction specified by the arrow. Connectedness in a digraph. Digraph here means directed graph. Connectedness in a digraph can be either strong or weak. Strongly connected. A digraph is said to be strongly connected if connected as a digraph following the arrows. Weakly connected. A digraph is said to be weakly connected if the underlying undirected graph is connected, ignoring the arrows. So this is a directed circle moving, that is go through a particular direction like that. That is directed circle, strongly connected, and that is weakly connected. Then we have other terminologies like emanate. An edge E connecting VAW is said to emanate from V. AV denotes the set of all edges emanating from V. Incident. An edge E, that is the edge E equals VW, is said to be incident to W. IW denotes the set of all edges incident to W. Out degree. The out degree of a vertex V is the number of edges emanating from V. In degree. The in degree of a vertex V is the number of edges incident to W. So this is a directed graph, and that is an undirected graph. Graph representation. For vertices in a graph, an array or a linked list can be used to represent them. For edges, any of the following can be used. You have the adjacency matrix, which is a two-dimensional array. You have the adjacency list, which is one-dimensional array of linked list. And you have linked list, which is one list only. Adjacency matrix. An adjacency matrix uses a two-dimensional array of dimension V by V for edges. For vertices, a one-dimensional array is used. That is an adjacency vertex. The presence or absence of an edge VW is indicated by the entry in row V, column W of the matrix. For an unweighted graph, Boolean values could be used, while for a weighted graph, the actual weights are used. This is an adjacency matrix. So you now have 1 to 1, F, that means they are not connected. 1 to 2 is connected. There's a direction. 1 to 3, I'm looking at the first table. True, there's a connection from 1 to 3. 1 to 4, F, no connection. 2 to 1, F. 2 to 2, F, no connection. 2 to 3, T, there's a connection. 2 to 4, T, there's a connection. 3 to 1, F. 3 to 2, F. 3 to 3, F. And 3 to 4, F. That means from the vertex 3, there's no connection to any other vertex. Other vertex connects to it. Then 4 to 1, true. 4 to 2, true. 4 to 3, true. And 4 to 4, F. Then we look at the other one. It has numbers. A to B, A to A, nothing is infinite. A to B, there's 10, that is the weight. Then A to C, 4. A to D, 1. B to A, no. B to B, no. B to C, no, which is infinite. And B to D, 15. C to A, no. C to B, no. C to C, no. C to D, 9. And then D to A, D to B, D to C, and D to D, nothing. They are all connected. Here are some notes on adjacency matrix. For undirected graph, the adjacency matrix is always symmetric. In a simple graph, all diagonal elements are 0. That means no edge from a vertex to itself. The space requirement of the adjacency matrix is O of n squared. Most of it is wasted for a graph with few edges because they will not utilize that space. However, entries in the matrix can be accessed directly. So that again is an adjacency matrix. Medina to Daman, to Riyadh, to Jeddah, to Aba. So we are also looking at the distance. Adjacency list. Adjacency list involves representing the set of vertices adjacent to each vertex as a list, and at the end we generate a set of lists, which can be implemented in different ways. We will represent vertices as a one-dimensional array and edges as an array of a linked list. The emanating edges of a vertex 1 will be in the list of the first element and so on. An adjacency list. You look at it 1, 2, 3, 4. From 1 you go to 2, 2 you go to 3, and then you now have again 4 like this. You now have 1, 2, 3, 4 as the vertex, 4 vertices. Then let's look at the edges. 1, 2 is linking 1, 3. 1, 2 is linking 1, 2, there's a link. Then after you get to 2, from 2 again, you go to 3. From 3, you go nowhere. Then you see again the edge from 2, you are going to 3. From the same 2, you are going to 4. And then after that, you are not going anywhere. Then there's an empty node after the 4. Then from 4, that is the 3 is empty. You are not moving from 3 to anywhere. That means that node is empty. Then from 4, you are moving to 1. From 4 again, you are moving to 2. And from 4, you are moving to 3. After that, empty. So that is the adjacency list. So you now see that it's implemented with the aid of a linked list. For simple list representation, vertices are represented as a one-dimensional array or a linked list, while edges are represented as one linked list with each edge containing the information about its two vertices. So you could see the vertices 1, 2, 3, 4. Then the edges are 1, 2, edges are 1 to 3, 2 to 3, 2 to 4, 4 to 1, 4 to 2, 4 to 3. But 3 to any vertex is not possible. You see that almost all of them are terminating in 3, but 3 is not going anywhere. So that is why you don't have 3 to any part there. In conclusion, very short, I think the 3 classes are supposed to be covered in one day. A stack is a data structure that follows the last in, first out. Queue follows first in, first out. Stacks and queues can be implemented using arrays and various linked lists. And as we know, just like a road along a path, Linked list, stacks, and queues are direct and easy ways to allow the free movement from one unit of data to the other. In summary, stacks and queues are a variety of data structures that requires you to add an element, and then you can remove another element to see if they are empty or see what to get if you remove an element. For stack, as you are removing the element, you are popping, you are adding, you are pushing. For queue, you are adding the element, you are moving it from the rear. And then when you are going to remove the element, you remove it from the front. The particular element you see depends on the structure. Stack gives you the element already there in the shortest period. A queue gives you the element already there in the longest period. Yes, what it means is that the element you are meeting at the top of the stack is the last one you just added. While the element you meet on the queue, as it is extending, the last one is far, far, far behind. So it is the longest period, the one that came last. And then your activities here, questions will be, what are the basic components of a graph? I feel you can answer that. What are the differences between directed going in one direction, undirected going in both directions, and weighted graphs? How is a connected graph different from a disconnected graph? And what is the adjacency matrix?